This is a really special treat for me because Stan Wilson, our speaker this evening, is someone that I've known since 1964. He came to Johns Hopkins as a graduate student. I had been there for 4 years. Another guy who was there at the time, Bill, when did you come? 61? 61. So we have 3 people who all got their PhDs from Johns Hopkins University from the Department of Oceanography. Bill is a professor at UC Irvine, and some of you here know him. And Stan came there. He had gotten a bachelor's degree at William and Mary, and then he had gotten a master's degree from the Virginia Institute of Marine Sciences. At that point, he was studying mostly fish. And those guys never know anything about mathematics or physics, so when he got to Johns Hopkins, he had to get a real education. And and he he did it in a masterful way, worked on waves. When he left Johns Hopkins, he went to work with the Office of Naval Research and was with the Navy for a number of years. He then went to NASA. And for the last 12 years, he's been at NOAA. And in every one of those situations, he has had a major role in shaping a scientific program that has been very important to this nation in terms of our ability to make critical measurements that are needed to understand what's happening to our planet, and with the hope that we can do a better job of managing it. And among the awards that he has won over the years. These are the only things I have to refer to my notes for. The National Science Foundation Antarctic Service Medal, the U.S. Navy Superior Civilian Service Award, the NASA Exceptional Scientific Achievement Medal, the American Geophysical Union Ocean Sciences Award, and there are many others. And so he operates at this interface of observation, data, information, science, application. And right now he's trying very hard to make sure that this country gets our observing system to the place where that it needs to be so we can catch up with some of the rest of the world. Because we very clearly have to understand the ocean, and we have it's divided among too many federal agencies, and it doesn't come together in any very neat way. So Stan tonight is going to talk about climate change and sea level rise. And Stan, it's great to have you with us.
Thanks, Jerry. Mike, working okay? Yep. Yeah. Great. Slide? No? Oh, there we go. We're fine. I'd like to acknowledge with special thanks Bill Patzert and Josh Willis at JPL here in Pasadena, and a whole bunch of additional colleagues without whom really couldn't have pulled this talk together. Global warming, question mark. With the current administration, I think we really need a question mark. And this is the political situation when you talk about global warming among some sectors of our society. Well, global warming is going on, and the Earth is round. And Al Gore has taken a lot of bad press for doing that wonderful movie, Inconvenient Truth. How many people have seen Inconvenient Truth? How many people have seen it twice? How many people have seen it 3 times? If my wife were here, she's seen it 3 times. I thought it was really well done. And so what I'd like to do is take, well, first I have to acknowledge the Nobel Committee for recognizing that, Al Gore speaks more than just, he doesn't speak with hot air and flames, etc. And so what I'd like to do is take part of his message and share with you some of the facts and the observations that we have. Global surface temperature averaged for our planet have increased over the last century by about 1 degree C, or about 1.6 or 7, 8 degrees Fahrenheit. So we observe global surface air temperature increasing. And we can look at, for example, global surface temperatures over the last 30 years, and you see it's quite variable, and you see that the continents are warming up more than the ocean. And you folks here in California are certainly seeing global warming in your surface air temperature, looking over the last 50 years. Some parts are cooling, and then you even see Los Angeles increasing a couple of degrees F. Of course, part of that is changing land use, an urban heat island. But get away from the metropolitan areas, and conditions are warming up here in your state. So the obvious question is, well, what causes global warming? Fossil fuel use for power and transportation is the greatest source of greenhouse gases that cause global warming. It all started, to kick in beginning of the Industrial Revolution, and then with the exploitation of petroleum in the last century, it's increased. Our CO2 measurements at Mauna Loa are increasing, and they're not just increasing linearly, but the rate of increase is increasing. There are other greenhouse gases besides CO2. There's methane, there's tropospheric ozone. Thank you, Jerry. So we've got CO2 as a greenhouse gas, methane, tropospheric ozone. And it's interesting to look at world population, this curve. You see it rising. And look at CO2 concentration in the atmosphere, and it's rising. It's also interesting, since we have a common axis, time, for both of these, is to plot them against each other to see what the relationship is. So this is world population versus CO2. And for the last 50 to 75 years, as the population has increased, CO2 has increased almost linearly. And more recently, we see the CO2 curve increasing faster than the population, reflecting more affluence in our world. So population's going up, CO2 is going up. So, what's causing it? The greenhouse effect. Well, what's the greenhouse effect? Sun radiates shortwave radiation, essentially in the visible, comes down to the surface. Some is reflected back from the surface, some's reflected from clouds before it gets to the surface. Some of it's absorbed by the ocean, evaporates water, and when the water vapor gets to high altitude, condenses. That's a source of rain. It also is a source of the fuel behind storms and hurricanes. And of course, some of that shortwave radiation gets to the surface and it's absorbed, and the surface warms up. Warm surface re-radiates at longer wavelengths, that is heat, and so there is heat radiation coming back. Now, when you increase CO2 concentration, or the concentration of other greenhouse gases, what happens is as the heat is radiating away from the surface, The greenhouse gases absorb that heat, or some of that heat, and then a fraction of that, when the greenhouse gases re-radiate, some of that comes back to the surface. And so if you increase the greenhouse gases, you increase the heat coming back to the surface. And of course, one of the questions is what happens to the additional heat that's trapped because of increasing greenhouse gases. So let's look at how much heat's involved. This is the UK Met Office global average temperature, surface air temperature. We like to compute how much heat that temperature change represents. So heat content is just nothing more than what's the temperature times what's the mass times the heat capacity. Let's focus on the heat capacity. Now, I'd like to, I couldn't get permission from the Aquarium to give this demonstration. And I think for obvious reasons when I continue. The heat capacity is absolutely critical. It's the amount of heat required to change an object's temperature by a particular amount. Let's take two balloons. This one's full of water. This one's full of air. Just lay a flame alongside a balloon that's full of air, and it pops. You apply the heat to the surface. Heat capacity of the air inside is pretty low, and so the rubber surface of the balloon heats up pretty quickly, very rapidly, melts, and a balloon pops. And this is where I couldn't get permission to use this demonstration here because there'd be water all over the place. But you get a balloon, fill it with water, and if you put it's pretty dramatic. If you put a flame against a balloon that's full of water, it'll take quite a while. It may be half a minute or it may be a minute, because the high heat capacity of the water takes the heat away from the rubber balloon. It keeps the rubber balloon surface, the surface of the balloon, cool enough so it doesn't melt and it doesn't pop. Now you hold it there long enough and obviously the water warms up and the thing's going to pop and you got water all over the place. But the main thing is that the oceans are the Earth's heat capacitors. So if we compute the heat that's gone into the atmosphere and the heat that's gone into the ocean, you see this is heat in the atmosphere that we're really one line width below zero. Over here we're really one line width above zero. And if we go back for that length of time for which we have reasonable approximation of the temperature distribution within the oceans, you see that the heat content of the ocean is really taken off. It's not increasing much in temperature, but the heat content is very high compared to the atmosphere. In fact, the atmospheric heat is about 20 times smaller. So where that heat goes is into the oceans. And in fact, for the last 40 years, 80 to 90% of the heat that has accumulated in the Earth's system because of increased concentrations of greenhouse gases is going into the oceans. And we have the oceans to thank for that. If this were not an ocean planet, the greenhouse gas would really kick in. So thank the oceans the next time you see them for being our heat capacitor for the Earth. So this is where the heat goes. So, got a bunch of heat going into the ocean, a bunch of heat going into the Earth system. Well, how does global warming impact the oceans? Well, I could go off in a number of different directions here, and I want to go in a particular direction. So I'll just mention a couple of avenues that I will not pursue that you may have had some lectures about, or maybe you will in the future. One is Oceans also absorb CO2, changing pH of the ocean, impact on coral reefs, as an example. Oceans also warm up, become more stratified, more difficult to get nutrients up to the surface, so potential impact on productivity. But we're not going to go there. We're going to go after the most obvious and easily understood impact on the oceans of global warming. What's the most obvious thing? It's sea level. So here's a record, last 125 years, 200 millimeter change, or about 8 inches. Sea level's gone up. So you say, oh, hey, that's about 1.8 millimeters a year. That's not too bad. But you can also look at this another way. Well, it was about 0.8 millimeters a year for this period, and it looks like 2 millimeters in this particular period, and about 3.2 millimeters per year in this period. This is the suggestion that the rate of sea level rise is increasing. I don't want to get into an argument. There's, in the scientific community, no, it's not accelerating. Prove it. No, it's not. And you just say, look at the record. There are certain segments to it. It looks like it's increasing. What sort of change in volume is that? Oops, I'm sorry, I'm going the wrong way. 16,000 cubic miles. Over the last 125 years, the ocean's volume has expanded. You could say, well, that's not too much. It's spread over the whole globe. So what's happening here in California? San Francisco, there's a record for the duration. It's about 8 inches in 100 years. San Diego and Los Angeles. Well, there's San Diego, the Scripps Pier. It's about 8 inches in 100 years. Oh, look, Long Beach, 3 inches in 100 years. Well, I'll have to get Jerry to comment if I don't get this right, since he comes from a part of the oceanographic community. I don't, the geologic side. How many people felt the earthquake yesterday? Okay. You live in a tectonically active area. One of the impacts of being in this tectonically active area is that land is rising. In fact, based on this observation, your rate of land rise is about 5 inches in 100 years. So if you got beach property, you're not going to be subjected to global sea level, the average global sea level rise, but it's going to be a lesser amount. I live in Baltimore in Chesapeake Bay, and there's if I went into, I don't want to go into details, but an impact of post-glacial rebound, our land is really sinking faster. And so we have the accumulated effect of sinking land and rising sea levels. So we're getting a lot of impacts in Chesapeake Bay, which you would not have as much of here. So how well do we understand global sea level rise? Well, what are the causes? Well, one is if you have a given body of water, you pump a bunch of heat into it, water expands. Another is you've got some additional fresh water that you're going to pour into it. Well, obviously that'll make sea level rise as well. And that equals total sea level rise. So we've got two effects that contribute to total sea level rise. So kind of how well can we sort this out? Well, if we're measuring the global oceans for heat, we have a program called Argo. I'll come back and I'll describe that. But this gives us estimates of how much heat is distributed throughout the global ice-free oceans. And if we want to look at the addition of fresh water, there is a pair of satellites currently flying called GRACE, and they measure changes in gravity. Basically, it's one satellite following another satellite, and they very accurately measure the rate at which these two satellites are drawn together or they separate. And so as the satellites come along, say to a big mountain's got more gravity. So the first satellite feels the effect of the mountain first and starts to speed up. And so the distance between the satellites lengthens. And after it goes over the mountain, the first satellite is pulled back so it slows down a little bit, and the second satellite speeds up. So by very accurately measuring the rates at which the satellites separate or come together, it's kind of like magic to me, but you can measure changes in the Earth's gravity. Then we have a way to measure total sea level rise. That's with a satellite altimeter. This is a satellite that is flying at about 850 or 900 miles up. It's got a radar, sends a pulse down, bounces off the surface, comes back up. You measure the travel time. If you know where the satellite is, we do that with the Global Positioning System, or GPS, which some of you may have in your cars, but you got them in your cell phones most likely. You can measure as a satellite flies along, pinging off the ocean surface. You can measure changes in the sea surface elevation to about an inch. That's an inch in 850 or 900 miles. This program and this program are both NASA, and they both run out of JPL. This program, U.S. effort, half the U.S. effort is run out of Scripps in San Diego. It's a collaborative program that involves 20-plus countries, and JASON is a collaborative program with the French Space Agency between NASA. So these are really, and then these two are really, international ventures where the scientific community has gotten together to say, let's collaborate and try to observe and measure, what's happening to the globe. Now let's take Argo and then Grace and then Jason, and let's sort of comment on each one. This is how an Argo Float works. It's about from here to here. It's about like so. Put an antenna on top. You drop it in the water, sinks to about a mile, drifts passively for 9 days, and it changes its ballast. It changes its buoyancy. It pumps oil from inside a pressure case to the outside, increases the displacement, rises to the surface, measuring the temperature and salinity, how hot the water is and how salty the water is. It gets up to the surface and it transmits this information to one of the NOAA polar orbiting satellites, and that transmits it to shore. And it takes maybe 12 hours to transmit data to the satellite, and then it sinks back down, and it drifts for another 9 days. And it does this for 3, 4, 5 years. There are 3,000 floats in a global ocean. Please don't be deceived. These are big dots relative to the size of a float. But the main thing is, this is the first, as of last November, when the array was complete, and now the array is being replenished as floats die. This is the first time we've been able to take the temperature of the global oceans in a realistic and representative way. So this global coverage we're really still within the first year of having a complete array. So this is how we measure the temperature of water. Now, don't bother yourself with the writing over here. Don't bother yourself with these wiggly lines right here. Up here you see the month and year. And this is essentially the temperature of a section of the ocean. Imagine we're standing out on the beach and we point up to Alaska. That's up here. And on the other hand, we point way down to the south to the Antarctic. That's down here. And so this is a section that runs right down the middle of the Pacific Ocean from Alaska to the Antarctic. And this is data collected from Argo floats in real time. And what to look for? Red is warm, blue is cool. And the main thing here, I mean, it's in a way, it's a really heavy scientific slide, but to me, it's also kind of an arm-waving slide. You don't have to understand the details to appreciate what we have. There's wintertime in the Northern Hemisphere, summertime in the Northern Hemisphere. Wintertime in the Northern Hemisphere when it cools, summertime in the Northern Hemisphere. And you can look over here, and it's the opposite of what's happening here. So it's summertime, wintertime, summertime, wintertime. But the point of this slide is we got a capability to measure globally for the first time within the last year of how the heat is distributed. Now let's talk about the addition of water. And just to clarify, water coming from melted ice. If we have sea ice, which is floating on water, and it melts, does not impact sea level rise. If we have ice, mountain glaciers, Greenland ice cap, Antarctic ice cap, that melts. It does raise sea level. And if that falls in, so does iceberg calving when you get a glacier coming off the land and pieces break off and drop in the ocean. So when we talk about the addition of water from melting ice, it's from melting land ice and calving from icebergs, glaciers. So when you hear about the diminishing Arctic ice pack, that's an impact of greenhouse warming in the Arctic, but it doesn't have any impact on sea level. However, the Greenland Ice Sheet, yes. In fact, observed on the surface of the Greenland Ice Sheet is meltwater pouring down through big cracks in the ice cap, and reasonable conjecture is you get water flowing down through the glacier, lubricating the bed, and this sucker can speed up and have an accelerated ice discharge. So I will come back and talk about the difficulty in predicting the impact of sea level rise, and it concerns the rate at which ice is being dropped into the ocean. So here are some results from NASA's GRACE or gravity satellite. This is gravity in a section across Greenland. You can see the seasons, but you can see just a uniform downward trend. And the northern part of Greenland is contributing maybe 0.15 millimeters a year, the southern part 0.45 millimeters a year. So all of Greenland is contributing based on these changes in gravity over April 2002 for the next 5 years of about 0.6 millimeters a year. So we think sea level is rising circa 3 millimeters a year. And Greenland alone looks like it's contributing maybe 0.6 millimeters a year, 0.6 out of 3. Let's now look at the Jason satellite altimeter. This is just a cartoon sketch frozen with regard to the satellite as it circles the Earth, and these are some positions of Argo floats. Since 1992, when satellite altimetry was introduced, there's 3 millimeters a year. There are a variety of satellites that carry altimeters, and you can see they provide a very consistent message about what the trend is. So we can start to put together some of these different observations from the different systems. So we can take, for example, global mean surface. What's the mean surface elevation of the ocean as a function of time? This is total sea level rise as measured by a satellite altimeter. Then we can go back and estimate what the temperature changes are within the ocean and see how much of this total sea level rise is due to thermal expansion. And you see it's about a third. The other 2/3 is due to melting ice. Now the GRACE gravity satellite started right here in 2003, so let's take a look at combining thermal expansion estimates with GRACE gravity estimates of the increase in mass of the ocean due to melting ice and see how they compare with total sea level rise. So blue is what the satellite altimeter tells us. That's total sea level rise. And green is addition of new fresh water based on gravity measurements, expansion of existing water due to Argo floats, due to thermal expansion. They line up. Our problem is Argo really only had its global array completed in the last year or so. GRACE has only been running for about the last 3 years, and so we're just on the verge of trying to sort out exactly how much of this is due, how much of the total sea level rise is due to the addition of heat, and how much of it is due to the addition of fresh water. But it certainly is very strongly suggestive, and maybe somebody will come back in 10 years and they'll tell you the rest of the story. But we're now beginning to put it all together. So, based on all that, how good are our projections of sea level rise? Intergovernmental Panel on Climate Change, or IPCC. This is an intergovernmental or UN, United Nations group. Leading experts, scientists from around the world gets together every 5 years and they do assessment reports. So the Intergovernmental Panel on Climate Change projects, this is the 4th assessment report, they project sea level to rise 30 to 80 centimeters by 2100. 30 to 80 centimeters. That's anywhere from 30 to 80. Now let's look at the curve. They have an envelope of estimated rise in sea level based on models. That's this gray cone. And then remember I said we weren't too certain about the rate at which ice is contributing to increases in sea level because of uncertainties in knowing how well the beds of glaciers are being lubricated and accelerated ice flow, etc. So the IPCC said, well, we need to add an additional land ice uncertainty. So that's this extra. So the IPCC projects sea level rise somewhere between here and here. And then you say, oh, well, how do their projections compare to what we actually observe? Well, that's what the satellite altimeter tells us. Satellite altimeter is tracking right along the upper bound. Observed sea level is rising at the upper limit of the earlier IPCC projection. So you look at that, I can imagine having an envelope of estimates, but when you're trying to estimate something and the thing you're trying to estimate is running along at the upper bound, that doesn't give me an awful, personally, I don't want to say anything bad about them, but personally it kind of gives me a problem that their range doesn't encompass what's happening. Then, with regard to uncertainties in IPCC projections, if you read the fine print of the synthesis report, which concerns this land ice uncertainty, hey, they say, quote, this is the fine print, the upper values that a range is given are not to be considered upper bounds for sea level rise. So it kind of bothers me that, okay, so this upper limit of the range is not the upper bound. Okay. What does that tell me? So they say 30 to 80, I'll bet you it's going to be a meter. And I would bet a good fraction of my retirement pay on that. And I'm not there yet. So then you can say, well, why are accurate projections important anyway? You're just getting, Stan, you're just getting excited about something. Well, worldwide, 146 million people live within 1 meter of mean high water. And the gross domestic product generated within 1 meter of mean high water globally is $1 trillion. Well, okay, fine, what about North America? 4 million people, ooh, that's only 140 billion GDP. And for those who are interested, the UK issued a report called the Stern Report on the Economics of Climate Change, and this was a document that the UK government, unlike ours, requested, saying, hey, we got climate change, global warming, we need to understand what some of the economic consequences of that so we know the extent to which you got to pay attention to it. So these are well attributed numbers. Well, the Nature Conservancy is concerned. This is a major wetland in North Carolina's Albemarle Peninsula. They ran an animation. Let's take 30 to 80 centimeters, which is what the IPCC said, and you're losing major wetlands, and of course the situation in Chesapeake Bay is going to be no different. So from there to there. Hey, what about if you live in Florida? Ooh, Hollywood, Florida. Impact of 1 meter rise above mean higher high water. You can go to that website. What they've done is they've gone around to coastal communities all around the U.S. and saying, 1 meter rise. How's this going to impact where people live and how many people are living in those places impacted? Hollywood, Florida, 140,000 people live in this area that is going to be directly impacted by rising sea level of only 1 meter. Miami Beach, oh, it's 88,000. Actually, for parts of Miami Beach, it could be just as well. Point Pleasant, New Jersey, oh, there's only 19,000 in this community. Hampton, Virginia, 146,000. And if you look at 1.25 meters, St. Petersburg, Florida, oh, we're starting to get up there. It's 250,000. And I'm going to come back and talk about this some more, but in San Mateo, there's only 23,000. Now I'd like to comment about the Bay Conservation and Development Commission. Does anybody know about BCDC here? Jerry? Fine, a couple of you. Bay Conservation and Development Commission is the first and is, I think, the first-rate coastal management organization in the United States. It was established in 1965 to stop the Corps of Engineers from filling in San Francisco Bay. And they were successful. And of course, a good bit got filled in beforehand. The estimate is water level rise in San Francisco Bay of nearly 1 meter by 2100 would inundate 200 square miles of land in development worth $100 billion. You can go to their website. It's got a, and if you're interested in this, they have, it's a wealth of information. San Francisco Airport's going to have to be diked. It'll be underwater. Oakland Airport have to be diked. It'll be underwater. And what BCDC has done, recognizing that they are not the unique agency that deals with global sea level rise matters, they have looked to other regional agencies to say, who else is involved? Well, there's the Association of Bay Area Governments, the Bay Area Air Quality Management District, and a Metropolitan Transportation Commission. Their goal, that is of the Bay Area Climate Protection Program, is to be a model for California, the nation, and the world. And in my opinion, they have achieved that goal with the limited work that they've done to date. And I usually don't like to read slides, but I'm really impressed by what they've done. They will develop a vision for San Francisco Bay to accommodate projected sea level rise and protect the most significant resources from flooding while continuing to enhance the productivity of the estuary. And steps that they will take, what I showed you a couple of slides back about, I think it was $100 billion is at risk. They will be in the process of determining the economic value of all resources to be impacted, estimate the cost of protecting the resources, and make decisions whether to remove or relocate or protect them. This is a model for the nation. Obviously, Rush Limbaugh, I'm not paying any attention. I think it's absolutely bizarre to overturn the world economy based on the musings of a few idiot leftist scientists is just stupid. That's what global warming is all about. He should go up to San Francisco. So how will sea level rise impact storm surges? You know, if you live in low-lying areas, it's really not sea level slowly creeping up and flooding you. But it's the storm surges that come on top of sea level rise, and it's how sea level rise exacerbates the storm surges. This is what BCDC says on their website. 12-inch increase in sea level rise would shift the 100-year storm surge-induced flood event to once every 10 years. Oh, so you say, well, okay. But what if you're a coastal engineer and your design criteria is I only want my property flooded or my facility flooded once in 100 years, and all of a sudden you find, oh my God, this thing's coming 10 times more frequently than I designed my structure for. But just to show you that there is some substance behind this, they've taken 100-year-long tide gauge record in San Francisco. They've plotted the frequency of flooding events for the first half of the 20th century. So that's how many times do you get a 3.8 meter flood, how many times do you get a 3.9 meter flood, etc. And the flooding events fall very nicely along this curve. So then you can say, well, okay, 100 years, you go up to 100 years. So a 100-year flooding event, well, it's going to be 4.3 meters or maybe 12, 13, 14 feet. Then they've taken the tide gauge record for the second half of the 20th century and the frequency of flooding events for the second half, and they run along this curve. And so what this shows is a 100-year flooding event for the first half of the last century has become a 10-year flooding event for the second. So you say, well, design criteria. Well, that was one of the problems in New Orleans. Levees, poor design criteria, inadequate attention. Of course, there was also inadequate maintenance. There was also development in the wetlands, flooding wetlands, consequent loss of wetlands, which are buffers against the hurricane storm surge. So it was loss of wetlands, inadequate design criteria for the levees, poor maintenance on the levees, and then you put Katrina on top of that, and you had this situation. It's not sea level rise on its own, but sea level rise is a significant factor. And 100 years from now, if we have sea level rising this much, you're going to see this, I fear, in a variety of places. What can we do about it? Not this. I was going to say I wish it were, but I can't say that as a federal employee. This is not an option. This is what too many people have been doing too long. This is not an option either. We do not need one more study to prove global warming. We need studies, we need observations, yes, but to understand what's happening to us, not proving something, understanding what's happening to us, what are the changes, what can we do to adapt or to retreat or to protect. There's a whole host of things we can do. As an individual, when you saw an inconvenient truth, energy conservation, reduce CO2 emissions, reduce the rate at which CO2 is increasing the greenhouse effect. Sea level is going to continue to rise, but we can slow the rate of rise of sea level. Compact fluorescence, drive less, walk more, recycle more, tire inflation, low flow shower heads. We don't need to package the heck out of things. Plant trees. Turn off your electronic devices instead of leaving them in standby. Go to this website. And for God's sake, how you vote is as important as driving a Prius, switching light bulbs to CFCs, raising the temperature for your air conditioning thermostat. It's very, very important to vote. We need very effective federal policies. You guys in California have got a remarkable governor in that he is really attuned, at least it seems to us on the East Coast, he's really attuned to global warming and climate change and trying to make a difference and do something about it. But when we come up to the elections in this November, is look at the candidate stands on the environment, on global warming, on climate change. Finally, my last slide, for additional information, I am stan.wilson@noaa.gov. I'll be happy to take any questions you might have. Here, so you can email me if you're like I am, I usually think of something the next day. Here is an absolutely remarkable book by Carrie Emanuel, What We Know About Climate Change. If you have a neighbor who really doesn't think it's happening, my wife likes this. I've gotten maybe half a dozen copies to give people. It's only 85 pages long. It is simple but not condescending. It's easy to understand. It's very, very well written. So that's one suggestion. And then the last suggestion is Gary Griggs will be here from UC Santa Cruz next Wednesday talking similar topic. And I'm sure he'll have a different complementary take on this. So with that, Jerry, I turn it back over to you.